Hey guys, day 2 of Trig. And look what we're going to talk about. Special right triangles. This is like geometry all over again. Yes! So the first part says you're going to use Pythagorean theorem to find the missing side for each part. I really don't think I should have to tell you how to do this, but as a quick reminder, it never hurts to remind you, in case you're watching this and you're sleepy or you've had amnesia or something. A squared plus b squared equals c squared, where we know the deal. A and b have to be the two legs of the right triangle. C has to be the hypotenuse. All right. So you can hit pause, quick calculate them all. I'd like to think you can rip through all of them, but the idea is just to see the pattern of what's going on. All right. So if we play the game and do, maybe the first one together, we would have 1 squared plus 1 squared equals c squared, which would give us 2. And then when you take the square root, c has the value of radical 2. Ta-da! And now when you do the next ones, you have to remember you're going to reduce. So if I do 2 squared plus 2 squared equals c squared, you will end up with this. I don't want you to leave it as radical 8. You would take the square root and break this back down into radical 4, radical 2. So this guy would come out as 2 radical 2. This one will come out 5 radical 2. As for the bottom row, as a quick reminder, if I go A, B, and C, 1 squared plus radical 3 squared equals c squared. Well, this is 1. When I square a radical, those are inverses. They just cancel. I get 3. And so I would get 4 equals c squared. Take the square root, comes out nice and pretty as 2. You're going to notice that the next one comes out nice and pretty as well. That'll be 4. The last one comes out as a nice integer value at 10. So what I was hoping that you would see is a reminder of something you already talked about last year in geometry, in that you see a pattern with the values. So for the first 3 triangles, you got 1, 1 radical 2, 2, 2, 2 radical 2, 5, 5, 5 radical 2. So a few things that I want you to take note of here. The fact that the 2 sides are always the same means we've got an isosceles right triangle. So down in the in general box here, because it's isosceles, that means those 2 sides are the same and also the base angles. So for those base angles to be the same, it has to be 45 and 45. The general rule is that these 2 sides are the same. I'm going to call them x, and the hypotenuse is just whatever x is times radical 2. So that's what's going to happen every time that we have a 45, 45, 90 triangle, which sometimes we'll even kind of reference like that. As for the other one, it might not be as obvious, but if you take a look, you've got side lengths here of 1, 1 radical 3, and 2, and then 2, 2 radical 3, 4, 5, 5 radical 3, and 10. So definitely a lot of radical 3s going on. And if we look, 1 to 2, 2 to 4, 5 to 10, the hypotenuse is always double that short side. So the way that we're going to show that, the shortest side is going to be x. The hypotenuse is double that, or 2x. And then the other side length is whatever the short side is times radical 3. So 1 radical 3, 2 radical 3. Here, this one is 5 radical 3. Or in general, we'll call it x radical 3. Now, the angles for this, I could go through and actually show you. So if you're curious, you let me know, and I could be happy to make a little video to show like where this comes from. But it actually gets derived from an equilateral triangle where you have all angles at 60. So this angle up top is 60, and then you end up bisecting one of the angles so that you're left with 30. So this is a 30, 60, 90 right triangle. Right? Specifically, the side across from the 30 is always the x, across from the 60 is the x radical 3, across from the 90 is the 2x. And yes, it's important where they are in that relationship. So some other quick reminders when we go to do some practice with this, we're going to be using these patterns to be able to quickly answer the side lengths without having to go through the calculation of doing Pythagorean theorem like what you did above. So as a little note, Yesterday's lesson addressed degrees to radians. So our conversion factor was 180 degrees is equivalent to pi radians. So with that being said, all the angles that we just mentioned here, 30, 60, 45, 90, those can all be written in terms of radians as well. So what I want you to think of is, all right, if I take 180 and divide it by 2 to get 90, I would take pi and divide it by 2. So 90 degrees is the same as pi over 2 radians. If we go from, sometimes it's easiest to go back to 180. If I go 180 and I want to talk about, 30 degrees, think about what do you have to divide by to get 30? I would have to divide by 6. So I'm going to do the same thing over here. I'm going to take pi, which is the same as 180, divided by 6. So 30 degrees is the same as pi over 6 radians. Right? And then see if you can challenge yourself to do the same thing with 60, same thing with 45. So think, what's 180 get divided by to turn into 60? You're going to do the same thing over here, and then we do the same thing for the 45. So hopefully you've had a moment to think. This one should be pi divided by 3. And then 45, since that's half a 90, you divide by 2 again, or really you're dividing by 4. All right. This is a good little thing to take note of because on the back, sometimes you're going to see degrees, sometimes you're going to see radians. Feel free to flip back and look if you need to. All right. But these are ones that you will have committed to memory soon enough. All right. On to the next page. So back up at the top, let's start with some simple ones. So if we start with one like number 1, if we look at what we have going on here, I want you to take note of the angles. It's a 30, 60, 90. So the relationship for the sides for 30, 60, 90, the side across from 30 is always x. The side across from 60 is always x radical 3. And the side across from 90, that's always 2x. So in this case, that just means that x is equal to 4, and now plug that in. So over here, this is 2 times 4, or 8. And then this side would simply just be 4 radical 3. As for number 2, now you're talking about a 45, 45, 90 right triangle. So in this case, different set of side relationships. So the two sides that are the legs are always x and x. The hypotenuse is always x radical 2. So since this side length is 10, that side length has to be 10 as well. And then the hypotenuse would be 10 radical 2. So you don't have to label it every time with the ratios. You could label it with a different color with the ratios if that helps. So when you go to do 3 and 4, now you have to recognize, all right, what angle are we talking about? So as a reminder, pi over 3, that's 180 divided by 3. That's 60 degrees. Pi over 6, that's the same as 180 divided by 6. That's 30 degrees. So down here, if you'd like to, write in, that's 30, which means the side across from that, that's going to be the x. This is 60. The side across from that is going to be the x radical 3. And then 90, side across from that's going to be 2x. And now take a look at what you have. The side that's the x, that's just 6. So now plug in 6 for the x's here and here. So this becomes 6 radical 3. Plug in a 6 here, that becomes 12. And then here, now we see the pi over 4s. Reminder, pi over 4, that's just 45 degrees. So if it helps, put the 45 in there so that you see it, and then write the ratios. So opposite the 45s are the x and x. The hypotenuse in this case is the x radical 2. So I think most of you could probably look at it and figure out what x is. But in the case where maybe you can't, set up an equation. Set x radical 2 equal to 5 radical 2. And then remember, these are just being multiplied together. So all you have to do is divide the radical 2 out. And there's your value of x. So if x is equal to 5, ta-da, 5 and 5, and that's it. You're done. A couple things. That's just theta. It's just a Greek letter that always represents an angle. The other one, that's just beta. So we usually use Greek letters to represent the angle measures, whereas we use like X and Y to represent the side lengths. Right? Just kind of helps clarify there. So what I want you to remember is that when you are labeling the triangle, you always go based off the angle that's being given. So theta in this case. So in terms of trig, the way we labeled the sides, this is the side opposite. Across from the 90, we reference as the hypotenuse. And the side next to it would be the adjacent side here. So I know I'm abbreviating. Feel free to write those words out completely if you want. So opposite, hypotenuse, and adjacent, or meaning next to side. I bring this up because you probably learned last year SOHCAHTOA, I'm going to guess, which is a great little mnemonic device to remember the ratios for sine, cosine, and theta. And what SOHCAHTOA, depending on how you learn to write it, you might have learned it this way, or maybe you learned it like this. So SOHCAHTOA. Right? This stood for the opposite side over the hypotenuse, the adjacent side over the hypotenuse, and then the opposite side over the adjacent. And the idea behind it was that for any set angle measure, the ratio of the side opposite over the hypotenuse side will always come out the same, no matter how big or small the triangle it is. And it's based on similar triangles, right? And your calculator has all those values programmed into it, you lucky dogs. So you always want to make sure when we start doing this, what mode you're in. Because if we use theta as a degree measure, then we're going to need to be in degree mode. If we use theta in radian measure, we'll need to be in radian mode, right? Otherwise, oops, I just remembered you got this little spot right here. So you can fill it in again if you'd like. Oops, O over H helps to write it incorrectly. So we can make that O over H. This is A over H, and this would be O over A. So down at the bottom, all the bottom is doing, really quick review, is just saying, could you tell me what the ratios are based on the triangle that you have here? I'm going to fix that really quick. Finally got some white out with me so that I could fix my errors here. All right. All right, so for this bottom one, the first row says find sine of theta. Second one says find sine of alpha. So for the ones with theta, I would label the triangle. Go start from theta, go opposite, across from the 90, hypotenuse, left over, adjacent. Or you could simply label them with O, A, and H. That would be fine too. Right? So you choose how you want to put those labels in there. All right, let's see if this is dry enough. Yeah, that'll work. Yay, over H. All right, so when we go to do sine, all you have to do is write the ratio. So the opposite over the hypotenuse is simply 4 over 5. Cosine, adjacent over hypotenuse, 3 over 5. Tangent, opposite over adjacent. And then when it comes to the alpha ones over here, now you would have to switch your labels. So I'm going to use a different color. So for alpha, the side of 3, that now becomes the opposite side. The 4 becomes the adjacent side. The hypotenuse never moves. So that's the easy part. So when you pick out sine, sine is now opposite over hypotenuse, or 3 over 5 in this case. Cosine, 4 over 5. Tangent, right, opposite over adjacent, is now 3 over 4. So a couple of things that you'll notice, or I hope you notice, is that sine and cosine, those ones matched for the opposite angles here. Same thing going on there. And what I'd want you to take note of is that theta plus alpha, those are the two acute angles in the right triangle. If all the angles together add up to 90, those two in particular, or add up, to 180, those two have to add up to 90, which are complementary. And so when we talk about sine and cosine, just think about the words written completely out. They're referred to as co-functions, which means they're equivalent when the angles are complementary. So there's a little geometry throwback, but some things that you'd want to also take note of, right, in this unit. In terms of tangent of this one and tangent of that one, those are reciprocals. So there's, another fun math fact, but nothing that we need to mention at the moment.